Assalamualaikum warahmatullahi wabarakatuh. Greetings, honorable thesis examiners, as well as Ibu Sekar Utami Setiastuti as my thesis supervisor. My name is Mohammad Arief Rajendra, an economics undergraduate student in the Faculty of Economics and Business of Universitas Gadjah Mada. In this video, I will present my bachelor's thesis titled Asymmetric Impact of Climate Policy Uncertainty on Renewable Energy Demand in the US, Evidence from a Threshold Autoregressive Model. Here we have the outline of today's presentation. And to introduce this topic, we first start with the background. Climate change has undoubtedly come to the forefront of global policy discussion due to its drastic risks and uncertainties pertaining to the economy and its relation to the environment. And because of that, there have been several climate initiatives that have been enacted, including the Kyoto Protocol of 1997, the Paris Agreement of 2015, as well as the COP26 in Glasgow in 2021. As for Indonesia, as an example of a developing country, the government aims to increase renewable energy consumption to 23% by 2025 in the General National Energy Plan. Despite this global commitment uh, and previous administrations, major uncertainties still occur in the context of the US. A significant amount of climate policies have been rolled back by the Trump administration, such as the withdrawal from the Paris Agreement and the reversion of the Clean Power Plan in the previous administration. And thus, the amplification of this uncertainty could affect consumers' decisions in using renewable energy. With that, we asked several research questions. The first being, does climate policy uncertainty affect consumption of renewable energy differently under different regimes of uncertainty thresholds? The second being, does higher climate policy uncertainty lead to decreases in the consumption of renewable energy beyond a certain threshold? Some research objectives include to examine the nonlinear effect of the CPU towards renewable energy consumption in the United States, as well as to analyze how the derived effects can be transformed into actionable insights for policymakers in the development of climate policies. Some research benefits include for the literature, since the nonlinear nexus between CPU and REC has yet to be discussed in the literature, this paper shall add the novelty and could become a reference point for future research in the subject matter. And policymakers and the policy side can ensure that the policies they enact and how they deliver it do not incur adverse or unwanted effects. It is also beneficial for developing countries to learn from the case of the United States and how uncertainty might affect their consumers' behavior in relation to consuming renewable energy. As for the literature review, we look into four of the most discussed papers throughout the thesis, as they directly look into the CPU or REC nexus. Of course, there are also other papers that look into REC, but we're going to look into the CPU REC nexus papers. To begin with, Shang et al. Modeled the relationship between CPU and REC using an ARDL model on data from the United States in order to find the short and long run impacts of CPU on REC. They found that the CPU does not impact REC on both the short and long run. Meanwhile, Cho et al., using a TSP VAR model, found that when allowing the model to be time varying, CPU positively affects oil prices and REC in most regimes. Lee et al. Performed a similar research using a VAR model with time varying rolling window bootstrap causality test to find causality between CPU and REC at different points in time. They found that the CPU REC nexus is both positive and negative, but depends on the government's attitudes towards carbon neutrality and climate change. Meanwhile, Shada Purchase and Go, unlike Shang et al., the authors considered the possible impacts of structural breaks on the modeling of the data, which has led them to use the Fourier augmentation above their ARDL model. And so they found that the CPU is negatively associated with REC in both the short and long run, in which they summarize as a wait and see policy, meaning that the consumers avoid renewables until a lack of clarity in the climate policy has subsided. As for the factors affecting REC, which will be used as the covariates in the model, we see that economic growth, be it proxied by GDP growth or the Industrial Productivity Index, is found to have significant effect towards REC and is expected to increase income and thus make renewable energy more accessible. Meanwhile, CO2 emissions are the main driver of renewable energy, as the mitigation of climate change is reliant on decreasing GHG, especially CO2. And according to Bhattacharya, it can act as a warning for economic actors regarding the status quo and climate change, and thus we should include this in the model. Finally, oil prices are also important, as increases in oil prices have been shown by previous studies to become a disincentive for consumers to purchase non renewable energy, and could lead to substitution for renewable energy, as found from the works of Brini et al., Sahu et al., and among others. Discussing the research methodology, we look into the TAR model, basically following Bunzel and Enders in 2010 to ascertain the we use a similar method to discern a difference in behavior with regards to the nexus between the two variables, namely using a threshold autoregressive model originally developed by Hao Tong and is specified as follows. We have the renewable energy consumption as the dependent variable, the climate policy uncertainty as the independent variable. We have the covariance of carbon dioxide emissions, the West Texas Intermediate crude oil price, as well as the index of industrial production, as well as the lag values of the REC. We also use logarithmic transforms and first or seasonal differencing, depending on which one would ensure that there is no non-stationarity. To acquire the threshold value, we follow the Biperon 1998 test of L plus 1 versus L sequentially determined thresholds. As for the estimation strategy, to begin with, we have the unit root tests. We use the standard unit root test for the initial test of stationarity to find the level of integration. We then use the Zivot-Andrews breakpoint unit root test to take into account of structural breaks that may be present in the data. We then use linearity tests to find whether the series are linear or nonlinear. So the first test we use is the Brock-Decker, Scheindman, and LeBaron BDS test, which is a portmanteau test for time-based dependence in a series and is useful for testing whether the residuals of the series are independent and identically distributed. We also complement this test with the MacLeod-Lee test, which is also a portmanteau test that uses autocorrelation function of the square of a time series to determine whether there are any significant autocorrelations in the time squared residuals derived from a linear equation. We then fit the TAR estimation, and after doing so, we must ensure that the model is stable and that it is robust to the lag of a threshold. However, when it comes to stability test, it's actually not necessary, as following the arguments from Tong and Lim, in their formulation of the TAR model, they defined the threshold model as a stabilizer of a nonlinear function, such that if a threshold model converges, it thus induces a stable recursion in the nonlinear model. And to find whether or not the model is robust to the lag of the threshold, we iterate the same models through different maximum lags in increasing intervals. So if we find a convergent model with a maximum lag of d, we iterate the same models with a maximum lag of d plus n to ensure its robustness. Here are the sources of all 7 variables that we're going to be using in the research, and the periodicity of the data is monthly data from April 1987 to August 2022, with the exception of the NVPU, which spans only from January 1990 to March 2019. So for the robustness checks, we are going to include 2 new variables, which are the environmental policy uncertainty as well as the household renewable energy consumption. So the ENVPU is an alternative to the CPU as discussed before. The main difference between the two is the word search strategies used by the author Noailly et al. In their construction of the ENVPU, as well as the algorithm in which they used the support vector machine algorithm to classify the observations that constitute uncertainty. We also include the household renewable energy consumption as a robustness check to see whether the effect of the CPU to the industrial REC is similar to the case of households, thus making the results more generalizable. We move into the empirical results. Looking into the descriptive statistics of all of the 7 variables, we see that nothing really sticks out, except of course for the kurtosis of the CPU, which will not persist as a problem because we're going to be using log transformations, so it's going to be normalized. As for the unit root tests, from the standard unit root test, we see that all variables seem to be stationary at I1, except for the ENVPU, which seems to be stationary at I0, if not taking into account for the KPSS test. However, for further certainty, we also use the Zivot-Andrews unit root test, and it also takes into account of structural breaks, and we find that the series are all stationary at I1, and this also holds true for the first difference STL decomposed series reported in the appendices. As for the linearity tests, from the BDS test of linearity, we observe that the test statistics are larger than the critical values, thus rejecting the null hypothesis that the series are linearly dependent. And to ensure the robustness of the previous results, we look into the MacLeod-Lee test, and we find that the test rejects the null hypothesis of linearity. Again, note that both of the results only imply nonlinearities exist within the series, but not necessarily the shape of the nonlinearity. As for the TAR estimation results, from the initial estimation, we find a significant nonlinear effect from the CPU to REC because of the fact that the effect of the CPU to REC differs under different regimes between the thresholds. A particularly interesting finding is that above the threshold, we see that the CPU has a negative significant effect to the REC, which could be interpreted as when the growth rate of the CPU at lag 15 is above or equal to 0.347%, a 1% increase in the CPU decreases REC by 0.042%, these findings are in support of Shed et al., Cho et al., and also Lee et al. As for the lag of the threshold, well, of course, 15 months seems quite a long lag. This could be interpreted as a time gap companies need to reach a conclusion whether or not to purchase and invest in renewable energy. The issue was also noted by Shed et al. And also Bhattacharya, as renewable energy consumption can be more capital intensive for producers and thus producing a larger lag. To test the robustness of the CPU REC nexus, we also estimate the household REC. We find that there does exist a threshold value, but the effect of the CPU to household REC is positive above the threshold, since a 1% increase in the CPU is associated with a 0.046% increase in the household REC above the threshold. So this goes against the previous findings as consumers display a just-in-case policy. Now, to add to the previous findings, we refer to Lee et al. And consider the possibility that government attitudes may affect the CPU to RC nexus. Recall that Berstike et al. And Basaglia et al. Noted that the CPU could not be examined purely through the variation in the index, as the context underlying the shock could have been inherently positive or negative, determined through whether the policies were in favor or against climate change mitigation. Since previous studies such as Wampler, Royd, and Blanchard, as well as Lee et al. Found that most administrations prior to the Trump presidency had generally similar attitudes for climate change mitigation, we approximate the effect of this dynamic by dropping the Trump administration observations in the next few iterations. So the findings were relatively similar, as the thresholds still persist. The main difference is that the CPU REC effect above the threshold becomes more positive for both cases, in which a 0.005 percentage point increase is observed for the industrial case, and a 0.046 percentage point is found for the household consumer case. The last robustness checks with the ENVPU, we found a significant nonlinear threshold effect. However, the ENVPU above the threshold is positively associated with the REC, as a 1% increase in the ENVPU is associated with a 0.024% increase in REC, which is of course different from the main results. So two aspects may explain the differences. The first is that the algorithm used to form the indices, as the CPU only used a naive word search algorithm, while the ENVPU used a support vector machine algorithm. The second is that the NVPU searches for a larger corpus of words in comparison to the CPU, thus allowing it to capture more articles. This led to the ENVPU having a larger recall rate. Otherwise, the percentage of actual positives identified correctly. And then Wiley et al. Also pointed out that the CPU's algorithm may lead to larger volatility, as shown in the left table. And if we recall the results of Lee et al. And observe the CPU itself, the larger spikes after the Trump administration could have induced negative CPU to REC association, and thus we should be careful of said results and rethink the use of the CPU. So to conclude, we found from our main estimations that there does exist a nonlinear threshold effect between CPU and REC, and the effect above the threshold is negative. While we found household REC also had threshold effects, the effect above the threshold was positive. And using the ENVPO as a robustness check, we also find that the effect above the threshold is positive. We consider some factors that in the formulation of the CPU and ENVPU and conclude that the ENVPU is more liable. We thus conclude that in accordance with Cho et al. And Lee et al., that CPU affects renewable energy positively above the threshold. Some limitations of this research include the fact that the first is the lack of capability to account for the context behind the shocks of the CPU index, as the index was not developed with sentiment analysis. And the second is that our suggestive evidence for the contextual effect of the policies on the CPU towards REC is in reference to Lee et al. And other political works. And this should be ideally done by having a separate index for positive or negative climate policy uncertainties, such as the indices used by Basaglia et al. And Brestike et al. Some implications include that policymakers should always aim to reduce or maintain climate policy uncertainty, and that if their respective country has the goal for carbon neutrality or increasing REC, then the enacted policies should be in favor of carbon neutrality. Some suggestions for future research is to incorporate analyses on positive and negative shocks to CPU to find how differing attitudes from government may affect renewable energy consumption, and that when developing the CPU index, future studies should also consider adding sentiment analysis with deep learning algorithms to ascertain the positive and negative climate policy uncertainty shocks above the SVM algorithm for classifying uncertainties. And now we have reached the end of my presentation. I thank you for your consideration, and I will see you on the exam day. Thank you.